Hello. I'm a bit late, I know, but we will start our lecture. I'm waiting just for you to say that you can hear me and you can see the video stream before I start. So today we're going to discuss about autoencoders and applications. Okay, so I'm still waiting for somebody to write in chat. Okay, so everything is fine. Great. So yeah, today we're going to discuss about autoencoders. So this is a deep neural architecture that is trained without supervision. So first we're going to discuss about unsupervised learning. So we're going to do a brief recap about one unsupervised learning, and then we were going to discuss about the general idea and the general concepts behind autoencoders. Then we will see specific examples of autoencoders. So we will start with undercomplete and overcomplete autoencoders, then convolutional autoencoders. We will also discuss about regularization using sparsely regularized autoencoders. And then we are also going to discuss about denoising autoencoders, stacked autoencoders, and contractive autoencoders. And then we will also discuss about one application in abnormal event detection. So I'm going to present in the end a recent work from our group that uses autoencoders to solve abnormal event detection in video. Okay, so this is the agenda for today. So first, let's start with unsupervised learning. So yeah, we also discussed about it last year at the practical machine learning course. So I'm just going to do a brief recap. So in unsupervised learning, we have data without labels, and the goal is to either cluster the data or to perform dimensionality reduction in order to obtain a better representation of the data. So we don't have any labels. We want to find some structures or patterns in the data without labels. So in the supervised, in the classic paradigm, the supervised learning paradigm, we have some data of pairs of input examples and labels. So we have data in the format X and Y. And the goal is to learn a mapping function F, which is infinite, from the domain X to the codomain Y. So, and this can take various forms. So this is a slide from actually a lecture that is going to be discussed in 2 or 3 weeks from now, which refers to object detection or object localization, classification, or we can also talk about segmentation. So all of these tasks are actually commonly approached using supervised learning. So in supervised learning, we have, I don't know, different labels. So for example, in localization, we need the object class and the bounding box for the respective class. For object detection, we have images annotated with bounding box and classes. And then for image segmentation, we have examples of objects with segments. But in each and every case, we have the labels that we want to reproduce. So in supervised learning, we have 2 canonical problems: classification, which can be done with different models, including deep neural networks, as you know, and also regression. So we have here various methods for regression, like linear regression, logistic, and so on. So in supervised learning, one question that can arise is what happens if we have missing values, or if we have incorrect labels for the examples, which is not such a big issue as what happens when we don't have any labels for training. So Actually, we are now in the second case where we don't have any labels. So this is unsupervised learning. So making the parallel with supervised learning. So here we have some data in the format of a set of examples X without any labels. So we don't have the Y here. And the goal is to learn structure of the data. So actually learn some correlations between features that could be meaningful in some way. So in the end, unsupervised learning can serve different purposes. So it can be used for clustering. So this is similar to classification, but without having the labels. It can also be used for compressing the data. So here actually in green, we have the applications of autoencoders. So I'm listing various examples where we can use unsupervised learning. And in green color, we see the applications of autoencoders. So these are compression, feature and representation learning, dimensionality reduction, and generative models. Okay, so yeah, this is the tasks that can be completed with can be done with autoencoders. So we know this is kind of similar to principal component analysis, meaning that we can apply principal component analysis to comprise the data. Of course, there we will lose some of the information. This also happens with autoencoders. When we compress the data, we lose some information. So it's a lossy compression. So essentially, even if autoencoders can do compression, they are not necessarily used for this. But as PCA, they can do compression. And once again, also PCA is not commonly used for compression. But they can be used for representation learning and dimensionality reduction. I never seen PCA applied as a generative model, so autoencoders have one extra case to be applied in, but anyway. So we start with the discussion with principal component analysis, because there is also a relation between autoencoders and PCA. So I'm not going to discuss too much about PCA. I'm just going to recall that what we do here, we project the data from a higher dimensional space to a lower dimensional space. And the components of this lower dimensional space are chosen in decreasing order of the eigen values. Which means that actually the first component that we project the data on has can explain most of the data. So actually the variation on this axis is the largest one. And then the second component is orthogonal to the first component and tries to, once again, also tries to explain as much of the data as possible, and so on. Okay, so that's all about PCA. So we discussed about PCA at the practical machine learning lecture last year. So you can check the slides if you want to see more about it. So I'm not going to discuss any more details. And just a reference here that with autoencoders. So this is a classic example of or let's say the simplest example of autoencoders, where we have feed-forward neural network in which the hidden layer has less units than the input and the output. And here the goal, when we train the autoencoders, we will explain this in more detail later. So we have some input data X. We project this data into some lower dimensional space, this Z vector here. And then we want to reconstruct the actual input. So we're going back to the same number of units as the input. So this is a traditional autoencoder. So using an autoencoder without activation functions for the neural units is equivalent to PCA. So this is demonstrated that we can actually perform, or we can learn PCA through a neural network without nonlinear activation. So if we add the nonlinearities, so if we add, for example, a sigmoid or I don't know, ReLU activation, then the autoencoder becomes nonlinear, and this means that it can project the data in a nonlinear space. So actually autoencoders, because of this, have more power to model nonlinear structure in the data. Okay, so autoencoders have been proposed since long time ago. So they are an idea that appeared decades ago in the history of neural networks. So traditionally, the application of autoencoders is to perform dimensionality reduction and unsupervised feature learning. So, for example, if we have only a few examples with labels and a lot of examples without labels, then what we can do is, for example, to train an autoencoder on the unlabeled data, and then use the latent representation as a feature representation for our supervised task, and then we can try to learn some linear classifier on top of this representation. So essentially it does dimensionality reduction and feature learning. But we also saw some connection recently with latent space modeling, and also in the direction of generative modeling. So it seems that autoencoders can also be used to generate examples, and we will discuss more about generative modeling in the next lecture. Okay, so yeah, one important thing to mention, I also mentioned it before, is that although autoencoders compress the original data into lower dimensional space, it is not commonly used for compression because the compression is lossy. So it's actually, we want to remove parts of the data that are not relevant for our task. So essentially we want to capture the big picture and not details that could be noise or other things. Okay, so going deeper into how autoencoders work. So we have here a data sample X without labels, and we would like to learn two functions, f and g, and these are called encoder and the decoder, and when we put them together, they form the autoencoder. So actually an autoencoder, essentially it autoencodes the input X by passing it through the encoder and the decoder. So it is formed of these two joint functions. So here the autoencoder is the function h, that is the decoder applied on the code produced by the encoder. Okay, so here the code is z. We also call it a code or a latent representation. So z is called latent representation or code. And here in this case we have a nonlinearity. It could be a sigmoid or another activation function that is applied on the input X, and we have some weights and some bias terms. So this is a typical fully connected neural layer that transforms the input X to an output Z, such that Z has, typically it has a lower dimension than X. Okay, and this is why commonly autoencoders are represented with this shape, because we expect that the input to be reduced in size. So this, in the end, we want to do dimensionality reduction. Okay, so then the decoder takes this latent representation Z and learns some weights such that it aims to reconstruct the input X. So here the reconstruction is denoted by x hat. So yeah, the full autoencoder here is the function h. So in the end, h is an approximation of the identity function, only that it's not actually trivial to learn this function h, because here the latent code is has a lower dimensional. So this is a bottleneck through which this information has to pass, and in order to be able to reconstruct the important details of fix, you need to reduce or to eliminate the unnecessary information in this bottleneck layer. Yeah, so this is the main idea of autoencoders. So here I think, yeah, maybe it would be better just to put this arrow somewhere either here or below. So let's put it like this first. Okay, so yeah, so x hat is called the reconstruction. So now going on to this idea. So what we're trying to do here is not really trivial, because we're not learning the identity function, as I said before. We're just trying to limit the number of hidden units. So this is important to remember. So in the end, what the autoencoder does is that the model is trying to capture the distribution of the data. So it's a data-specific model. Okay, in order to train the model, we use, as in a classic neural network, we use gradient descent. So this is a classic, the classic way to train as any other fully connected neural network. And here we actually use the typical loss is the squared error loss, and sometimes we can also use the absolute error loss, or these are also known as the L1 loss or the L2 loss. So essentially what we do here, we compute the difference between the squared between the components in X and the components in X hat, and we sum up the results, and this is or we average the results, and this is the value for the loss function. So this is how it is typically done. Now we can also use, in some modern approaches, we can also use cross entropy, especially if the input and the output vectors are interpreted as probabilities. So if the input is between 0 and 1, essentially we can also use cross entropy as a loss function here. But you need to be careful with it, because in practice it might happen. So if it's not suitable for the problem, then cross entropy might not be a good choice for the loss function. Okay, so in some cases it can work better than the squared loss, and in some other cases it might not work at all. So you have to be careful when you decide which loss function to use. And yeah, for the basic autoencoders, we distinguish between two types. We have undercomplete autoencoders and overcomplete autoencoders. So actually what I discussed so far and what I presented to you is the most commonly used type of autoencoder, which is undercomplete. So undercomplete means that in the bottleneck layer, in the latent layer, we have a latent representation that has less components than the input, whereas for overcomplete autoencoders, we have a representation, a latent representation with a higher dimension. So there are also applications of autoencoders in which we want to embed, for example, the data in a higher dimensional space. So we can also use autoencoders for this, but we have to be careful with their use, because in this case, the autoencoder can learn some form of the identity function, and we do not want to simply learn the identity function. So here, in order to be able to train these overcomplete autoencoders, we typically add a regularization term on top of the latent representation. And we will discuss more about regularization when we discuss about sparsely regulated autoencoders, and also when we discuss about contractive autoencoders. Okay, so in the typical autoencoders, where the middle layer has is a bottleneck layer, it essentially compresses the input, and it is useful to model the training distribution. So it is essentially capturing the training distribution, and this is one aspect that is actually used in the abnormal event detection application. So because so we rely on this fact actually. So if we want to do anomaly detection, we do not have supervised data to train the model. We only have normal examples. So we learn an autoencoders on the normal examples, and we assume that it will learn only the training distribution. And then when we apply the model at test time, when we encounter an abnormal example, then the label the reconstruction should be worse for this example because it's outside the distribution, and then we can label examples as abnormal if the reconstruction is higher. Okay, so this is the basic intuition for the application. So we will discuss more about this later. And yeah, so usually the hidden nodes are good features to represent the training distributions, and bad for other types of input. So this is also related to what I said before. So let me just check if there are any questions. No questions. Okay. So next we discuss about overcomplete autoencoders. So here in the overcomplete autoencoders we have more components in the latent representation. So there is no compression here. So essentially each hidden unit could copy a different input component. And there is no guarantee here that the hidden units will extract meaningful information. So in order to guarantee this fact, we need to add regularization here. And as I said before, we will discuss more about regularization later. So typical applications of this type of autoencoders is when we want to do dimensionality, to embed the data into a higher dimensional space. So for example, if we want to solve, I don't know, the XOR problem from a 2D space, we can embed the data into a higher dimensional space using an autoencoder, and hopefully we can learn some linear classifier in this new embedding space. Okay, so we also have an example here in the slides, so where you can see how autoencoders are trained and how they converged. So I checked the link today, so it's still good. So let me refresh here, and yeah, you can see here in this web page how an autoencoder is optimized on the MNIST dataset. And after a few iterations, you will see that it will start to, so this is a projection of the learned manifold in a two-dimensional space where you can see the examples. And as the model converges, you will see that it will start to cluster similar examples together. So we already see that the ones have started to form a group here in the lower part of the image. Yeah, I think we really need to wait maybe a few more iterations in order for for the autoencoder to form some meaningful clusters. Yeah, so I see here, so there are some groups of 3s and 8s here. The ones are grouped around here. We have the 0s grouped here on top. We have the 4s that are typically grouped in this area, and this is also grouped with similar letters like 9 and 7 that are kind of close. The 5 seems to be somewhere in the middle now. Yeah, and actually you see how the model converges. Yeah, and we also have the value of the loss function here. Yeah, so I will let it here I'll leave it to run a few more iterations, and probably we will come back later to this representation and see how the data is grouped in the end. So I think we can really see here now the clusters with 9, 4, 0, 1, 3s are around this part. Yeah, so let it run for a few more iterations. Okay, so this is a nice example for you to follow. So the main idea with autoencoders is that we can also do some interesting applications with them. So for example, if we have two input examples from different classes, it seems that the latent space representation is uniform and it can be traversed using, I don't know, interpolation between two examples. So in this example, we have a 0 and a 9. So these are taken from the data set. We pass them from to the encoder, and here we obtain the latent representation. So the latent representation has 4 components by 8 components. So it is represented as a matrix, but either way we can, doesn't matter, it can be a vector or any representation that is smaller than the input. So here the images are 28 by 28. The output is 4 by 8. So this is a contractive, this is an undercomplete autoencoder that compresses the information. So here we have these vectors. And what we can do, as I said before, we can do interpolation in the latent space, obtain a new latent vector, and then once we pass it through the decoder, then we can obtain some interesting results. So actually, I'm asking you, can you guess what the output will be here? Let me see if I see. Okay, don't see any answer. I'm not sure about the delay. Meanwhile, I'm also trying to see this example with ones. Here I think it's the cluster with 3s became more visible, and also the cluster of 0s. Here we also see the 6s that started to cluster together, the 4s, and so on. Yeah, and we also see some examples of the input and reconstruction. So here, this is, I think, this is still has a few epochs to converge. So the reconstructions do not look so good. So the model is still converging and still learning. But even now we see some useful clusters here in the data. Okay, so we have one answer here. So yeah, actually it is a continuous combination of the 2 digits. So the output looks something like this. So We have this from 0, it goes progressively to 9, and here we have a different example that goes to a 4, so from 0 to 4. And yeah, in the middle we have combinations of these two extreme examples. So interestingly, yeah, you can do latent space interpolation. So this is just an example with digits, but you can achieve these interesting results with any type of data, images, and so on. You can interpolate images in the latent space and obtain some useful information. Okay, so next we're going to discuss about different types of autoencoders. So one type that is very used nowadays is convolutional autoencoders. So essentially a convolutional autoencoders replaces the fully connected layers with convolutional layers. Perhaps one interesting question here is how do we apply the convolution to increase the latent space representation to a higher dimensional space. So this is a new way to new layer to introduce now. Actually, this can be done in two ways. There is the convolutional layer, and we can also do upsampling and then convolution. So we're showing a convolutional autoencoder for the MNIST database. So in this case, the input and the output have 28 by 28 pixels. And here in the encoder, we have convolution and max pooling operations. This is the latent space code, which has a lower dimensional representation compared to the input, and here we have the convolution and upsampling operations. So these are applied that can be applied in the decoder. Okay, so the new operation that we're doing here in the decoder in order to increase the input is called transposed convolution or deconvolution. So here we have an example where the convolution is applied on a 4x4 input, and the convolution uses a 3x3 kernel. So from a 3x3 kernel we obtain an output, and if we apply it 4 times here with a stride 1 and valid padding, then we will obtain an output that is twice as smaller. So the equivalent operation that increases the input is based on the same idea. So in this case, what we do using the same parameters, stride 1 and padding valid, in order to obtain this output, we actually add padding to the input, and then we can obtain the higher dimensional output. So this is essentially obtained just by increasing the padding in this case, but in the more general case, actually when we have a larger stride, then the input uses is actually kind of dilated into this space. So then when we apply the convolution on top of it, we obtain these results. So here we have 5x5 output and a 2x2 a 5x5 input for the convolution and a 2x2 output. So here we have 3x3 kernels and stride 2, and the reverse operation. So here we need to to add this. So with stride 1, these are just stuck together. When we use stride 2 here, we actually add a space between the input, and then we apply convolution with 3x3 kernel and obtain this output. So in both cases we see that the padding here is 2 in all directions, and we can also do this. So if we change the padding to same, so in this case we have padding of 1, the kernels are 3x3, and we use a stride of 2, and accordingly we will have 5x5 input that is reduced to a 3x3 output. And for the deconvolution operation, the 3x3 output is organized on this grid like this, and then when we apply the convolution with 3x3, it results in this activation map of 5x5. Okay, so this is the relation between the convolution and the reversed operation, which is the deconvolution. And this can also be achieved by doing upsampling and then classic convolution with padding same. So this can be implemented either as a single operation, which is called transpose convolution, or two operations, upsampling and then convolution. Okay, so if we train convolutional autoencoders on the MNIST database, we can use the representation in the latent space to cluster the examples, and we will obtain a very good accuracy on the validation set. So applying convolutional autoencoders on MNIST gives an accuracy of about 88%. So yeah, I'm going back to this example. So I think we have some interesting clusters. We also see a cluster with 7s here and so on. I'm going to close this now because it takes a lot of my processing power, and the computer starts to make this noise, so I just close that window. Okay, so yeah, so this is what happens when we apply convolutional autoencoders. We get good accuracy rates on the MNIST database. And okay, now we discuss a bit about regularization. So if we want to force the autoencoders to learn more meaningful features without altering the code dimension, this can be overcomplete or undercomplete. So in both cases actually we can use regularization, but it is most recommended for overcomplete autoencoders. So yeah, the solution is to add regularization. So this means that we impose an additional constraint on the network. And here we start with this example without regularization that shows these dense activation maps that actually model, in many cases they model more than one digit. So and they model the entire digit. So this is a very dense autoencoder, and in order to make it more sparse, we add this regularization parameter. So in the end, what we want to achieve is to obtain these sparse activation maps that can be combined together using some linear combination and obtain the digit that we want. So this is the idea behind sparse autoencoders, and the way to induce this type of activation maps is to add regularization to the loss function. Okay, so how we do this is, let's introduce some notations first. So we consider the activation of the j of the hidden unit at index j in the bottleneck layer as aj. So bn stands for bottleneck. And we also consider, so this is the value of this is the activation function with parameters and so on. And we also have here the output of the activation function for an input x. So this notation aj of x is the output of the activation function of the unit j from the bottleneck layer on the input x. Okay. So now we introduce this additional notation. So here we have m data samples. So as we pass these m data samples through x, we have here x1, x2, xm. So these are data samples that are given, or actually inputs that are given to this activation function of the unit j. We obtain different activation values here, and when we do the sum and divide by m, so this is equivalent to the average of the activation values for this unit here. So we denote this average activation with the notation rho hat of j. So this is the average of activation of the hidden unit j. Okay, so this is computed from the data, from the training data that we have at our disposal. So now, in order to introduce regularization, is we want to force this average activation to have a specific value. So this is called a sparsity parameter. So we want to introduce this parameter. And typically, if we want to introduce more sparsity, we want to make the average activation smaller. Okay, so this is typically small, but we can also try to see what are, I don't know, the values without regularization to get these estimates, and then we can try to reduce them by imposing this this additional constraint. Okay, so the constraint is we want this average activation of each neuron j to be close to rho, and the way to impose this is we need to add a penalty term when the average activation deviates from our target rho. So here we can use different penalty terms. So one of the most common ideas is to use the Kullback-Leibler divergence between this average activation and the actual target activation, which is computed as a sum of all the activations over all the units in the bottleneck layer. So this is actually the regularization term that we add to our loss function. And here we have an interpretation of the Kullback-Leibler divergence. So if this is equal to if the average activation is equal to the desired activation, then we will have divergence equal to 0. If we have if our predictions are higher, then the divergence increases, and if the predictions are smaller, the divergence also increases, but not as bad. So essentially our goal is to make sure that the average activation is smaller than rho. So if it is smaller, it's not that bad, but if it is higher, we have a higher divergence here, and we need to optimize the autoencoder. So we have a greater penalty if the average activation is higher than if the average activation is lower. Okay, so this is a graphical interpretation of the Kullback-Leibler divergence. So just a short deviation of how you compute the Kullback-Leibler divergence for two distributions. So here we have this example of distribution P and Q, and they have different distributions for beans 0, 1, and 2. And here we see the actual values and the way to compute the Kullback-Leibler divergence between P and Q. So it is the sum of P, so the probability of sample X. So in this case, we take all these beans one by one. So here P of X is 0.36. And here we have the natural logarithm of P of X divided by Q of X. So we do this for all the components, and we can compute the divergence between P and Q. And this is also a note that this divergence is not symmetrical. So if we compute the divergence between Q and P, we will obtain a different value. Okay, so in the end, our objective for the autoencoder is to learn a good representation. So this is the original objective. And here we add the sparse regularization term with the Kullback-Leibler divergence. And this is also controlled by this parameter beta, which actually controls how important is to obtain sparse representations versus how important is to reconstruct the actual input. So it controls how much regularization we want to add to our model. Okay, and one important note here is that we need to compute here at every step and every forward pass this average activation of our model. So it could mean that it requires some additional steps compared to regular autoencoders without regularization terms. Okay, so yeah, so this is the another type of autoencoder that is called sparsely regulated autoencoder. And next we're going to discuss about denoising autoencoders. Yeah, so I think yeah, the noise, yeah, just the computer stopped running that autoencoder in the web page, so now noise is out. Okay, so going on with denoising autoencoders. So here the intuition is the same. We still want to encode the input without reproducing the identity function, but we also want to undo the effect of corruption that is stochastically applied to the input. So what we want to do here is to have an encoder that takes noisy input. It encodes it into a latent space representation, and then when we decode this input, we obtain the input without noise. Okay, I'm sorry, I had to maybe not move this like this, just this part. Okay. Okay, so in the end we obtain the denoised input. Okay, so this is one way to achieve a robust representation, and it also works like some sort of regularization. So one type of application is with the denoising autoencoders is to use this noisy input to train the encoder, and then we use the latent space representation as input to a neural network classifier. Then we have here some supervised problem that we train this part of the network. And actually, we can also train it end to end. Okay, so this is the main use case for denoising autoencoder. They are not necessarily used for denoising data, so the results are not typically that good. But it has alternatives, so it has different applications. Okay, so in a classic, so what's the difference then with classic autoencoders? Well, in classic autoencoders, we have the input X and the output of the autoencoder, which is G of f of X. And we have some loss function that gives us the reconstruction error between X and X hat. So in a denoising autoencoder, here we have X tilde, which is a copy, a noisy copy of the input X, and when we compute the loss, we compute it with respect to X, not with respect to the noisy input. So this means that the autoencoder takes a noisy input, but it is forced to reproduce the input without the noise. So yeah, the main idea is we apply this autoencoder in order to obtain a robust representation against noise. And the noise can be, I don't know, Gaussian additive noise that is added over the image. So assuming that this is the input image, we obtain this image with noise that is given as input to the autoencoder. Okay, but the trick is, as I said before, it's not directly given as input to the encoder. So when we add the noise here, we still keep a copy of the original example X, and we compute the loss between X hat and X, but actually the encoder takes as input only X tilde. Okay, so how this works? So we have the input X, we apply some noise on top of it, and then we obtain the noisy example, and this is given as input to the encoder. So here we apply the encoder and the decoder, and we obtain the denoised output. Okay, so this is X hat, and then we compare X hat with the original input X. Okay, so this is the main difference between denoising autoencoders. So it's not only that we're adding noise to the input data, we're also measuring the loss with respect to the original input, not with respect to the input with noise. So essentially, yeah, the autoencoder is forced to remove the noise in order to achieve a good loss value. Okay, so the main idea with autoencoders is that if we have some corrupted input, we add variation on the data, and we learn to better project the points on this nonlinear manifold. So this black line is the nonlinear manifold learned by the autoencoder, And as I said before, SPCA does some projection of the data onto this linear manifold. So this is a nonlinear manifold for autoencoders, and corrupting the data improves the generalization capacity of the autoencoder. So it's actually adds more variation in the original input space. Okay, so yeah, it learns to project some noisy input to an example on this manifold. And here, if we add this type of autoencoder on MNIST, the accuracy on the validation data set grows to 92%. So it's a 4% increase in terms of accuracy. So this type of autoencoder seems to produce better results. And we see here that this result was reported with a noise factor of 0.5. So this is how the inputs look like, and these are the corresponding reconstructions. Yeah, so mainly the denoising autoencoder is trying to solve a more difficult task, and in solving this task it achieves better accuracy in finding good clustering of the data samples. Okay, so next we discuss about stacked autoencoders, and of course we also have combinations such as stacked denoising autoencoders and so on. So this combination is possible. Okay, so the motivation to use stacked autoencoders is regarded to the application. So typically we want to obtain high quality features from autoencoders. Then we can so essentially the main application of stacked denoising autoencoders is to learn is to do representation learning. Okay, so we want to learn some useful representation of the data. Okay. Okay, so this is mainly related to the application, and also related to the training process. So it is still stacked autoencoder means that we're learning the autoencoder layer by layer, and we use the layers from the previous autoencoder that was trained. Okay, so essentially we have once we train the autoencoders, we keep all the autoencoder layers and we use them as I don't know, pre-trained layers in any supervised classifier. Okay, so the pipeline is we have the input X, we have the stacked autoencoder, then we add some classifier on top of it, and then we have the output Y. And here we explain, so this is the most important part of stacked autoencoders, is about the training process. So we start with an autoencoder with a single layer. So we train the autoencoder to model the input X to some output Z1, and then we want to reconstruct the input X through this output X hat. So we train this autoencoder, then we remove the decoder, we keep this part, we add another autoencoder, so this is the stacking part. Now we want to learn this, so we train this autoencoder independently. So this autoencoder encodes the examples in Z1 into this latent space Z2 and then tries to reconstruct the input. So this is trained independently, and then we also keep this part, and here we can add more steps for the stacked autoencoder. So we train it layer by layer, we keep these pre-trained layers, and then we add the classifier on top of it, and we reproduce the output. So this is how stacked autoencoders work like. Here actually, yeah, this is the original training process. Now actually we can train the autoencoders, the stacked autoencoders jointly. So we can also have here a decoder, another decoder, and we can actually add a loss term such that this intermediate representation becomes equal to this intermediate representation, and this intermediate representation becomes equal to this intermediate representation, and so on. So it's actually, it becomes like a classic autoencoder with several layers, only that we impose the constraint that each corresponding layer produce the same output. So this is the idea behind stacked autoencoders, and their main application is to do representation learning and to be used in a classification model where we do not have sufficient labeled examples to train the whole architecture. Okay, so yeah, this is about stacked autoencoders. Now we discuss about contractive autoencoders. Okay, so here we have yeah, so the answer is yes. So for the Kullback library divergence, I've shown the graph, so I'm going back a few slides. Okay, so yeah, actually I'm not sure if you can see this graph so well because it's a very slim line here, but the Kullback library divergence looks something like this. So the function is continuous, so it can be used into the loss function without problems. Okay, so this is the shape of the loss function. So as the average activation is close to the target, then the Kullback library divergence is close to 0, and then here it can increase. So it's not symmetrical as I explained in this example, so this is why it looks like this. So we use it like this, because if the activations are smaller, then this can only mean that the autoencoders are more sparse than what we want. So we are okay with that. But if they are not sparse enough, here we have a higher loss value. Okay, so the answer is for Mihai is yes. Okay, so we were somewhere at, so we were at contractive. Okay, so contractive autoencoders. Okay, so overcomplete autoencoders with regularization are called contractive autoencoders. So contractive autoencoders are typically have a higher dimensional latent space than the input, but they also have a regularization term that is added to the loss function that limits the norm or the magnitude of the weights in the hidden layer. Okay, so the main idea with contractive autoencoders is we want to extract features that reflect variations in the training data, and we want to make it invariant to other variations. Okay, so we just want to, for example, if the training data um, uh, can have, I don't know, different rotations, then we can reflect this in the autoencoder as, I don't know, if the data doesn't have, let's say, noise variation, then we do not want to account for this model. So we want the model to be invariant to noise, but it should be variant, let's say, to rotations. Okay, so in the end, we want to so points that are close to each other in the input space, they want to maintain this property. So they should be projected in different locations if we have variation in the training data with respect to the two inputs, and if we have other variations, then the two inputs that are not seen in the training data, then the two inputs should be projected in the same location. Okay, and the way to add this regularization term is to actually use the Frobenius norm of the Jacobian matrix. So here we I'm not the one to introduce these concepts, but I should at least remind you about them. So the Frobenius norm, or the L2 norm of matrix A, is equivalent to the square root of the sum of all the components in the matrix A of I and J that are raised to the power 2. So we take all the, it's just like the norm of a vector, right? But we, instead of applying it on a vector, we apply it on the whole matrix at once. And yeah, the Jacobian matrix of a function f with respect to x, where x is a matrix. It contains all the partial derivatives of the function f with respect to each component x. So this is the Jacobian matrix, and our loss function for contractive autoencoders is the Frobenius norm of the Jacobian matrix. So this is the component omega of x. So this is equivalent to the sum of all these components in the Jacobian matrix raised to the power of 2, and also we add the square root of this sum. Okay, so we also have here a regularization term, lambda, that controls the balance between the reconstruction objective and the flatness of the hidden layer. So this is the gradients well, with respect to the hidden layer. So if we want to keep the norm of this gradient small, then the hidden layer needs to be flat. So the way to control this is if we have if we want to have a good reconstruction, then we use lambda equal to 0 or close to 0, then we will have good reconstruction. Otherwise, if we want to make sure that the hidden layer is flat, so this means that actually we throw away as much information as possible, then we can increase lambda to, I don't know, infinity. So yeah, during the optimization, the model will give more importance to reducing the Frobenius norm of the Jacobian matrix. So if we combine these, so if we find the right lambda, then we will have an autoencoder that keeps only the good information, even if the autoencoder is overcomplete. So this term really ensures that The autoencoder will not learn the identity function even if the latent space is overcomplete. And here, yeah, we illustrate the example. So we have samples, the same sample that is rotated with contractive autoencoders. The rotated samples will be projected in different locations of the nonlinear manifold, but there will be probably organized according to how the rotation is made. So if we rotate in this direction, we expect that the examples will be on this side. If we rotate on the other direction, the samples will be on the other side. So the encoder must be sensitive to this variation in order to reconstruct data samples in the input, but it doesn't need to be sensitive to variations like noise or something else that is not observed in the training data. Okay, so this is about the contractive autoencoders. So yeah, we discussed about these denoising autoencoders and contractive autoencoders. So these are essentially trying to do the same thing. So they want to improve the generalization capacity of the autoencoder. With denoising autoencoder, well, the model is easier to apply and perhaps easier to understand. So denoising autoencoder make the reconstruction function resist small perturbations and finite size perturbations in the input, whereas contractive autoencoders make the feature encoding resist small perturbations. So this is the regularization is with respect to the feature encoding, and for denoising autoencoders, the model is forced to resist these perturbations in the input with respect to the reconstruction. For denoising autoencoders, we have some advantages, such as it doesn't require so much additional code on top of a regular autoencoder. So just you add some noise to the input data sample before giving it as input to a regular autoencoder, and then you just have the denoising autoencoder. So you don't need to compute this Jacobian of the hidden layer, which also may take additional time during training. But for contractive, sorry, for contractive autoencoder, we have a gradient that is more deterministic. So in the end, we might get more stable results than denoising autoencoders. And it also has one less hyperparameter to tune. Okay, and some applications of autoencoders. So the first application, which is quite simple to do, and it is quite a nice application and not so complicated, is to apply autoencoders for image colorization. So essentially, you give it as input a black and white image, and you train to produce color images. And this is the input, this is the target output, and the network can learn to reconstruct, for example, outputs like this. That look quite realistic. So this is one nice applications of autoencoder. They can also be used, for example, for watermark removal. So from this photograph with a watermark on top, we obtain this photograph, and Another application that I was mentioning at the beginning is to apply autoencoders for abnormal event detection. So this work was published at CVPR in 2019, but the results are still state of the art or close to the state of the art. So it's another interesting applications of autoencoders. So let me just see how much time we still have. Okay, so yeah, I'm trying to finish probably in about 20 minutes. So first I'm going to introduce the problem. So this is a very challenging problem because abnormal event is really hard to define without considering the context of the respective event. So we have two examples. So it's not just action recognition, okay? So for example, action recognition is, okay, we'll see a car that is driving, so we recognize this action. So it's not as easy as that. It also depends where this action is happening. So for example, if a car is driving on the street, that is labeled as a perfectly normal event. But if the car is driving in a pedestrian area, then this is forbidden. It shouldn't happen. So this would be labeled as an abnormal event. Another example is a person that is, I don't know, running on some sports court versus person running from outside the bank. The action again is the same, a person running, but the context makes us label the two events as normal or abnormal. So depending on the context, the same action can have different labels. Okay, and so there is this reliance on context, and also anomalies are hard to find and hard to collect examples. So and this is because if we want to have realistic anomalies, well, in some cases we might not have examples at all. And if we want to produce some examples, so for example, we want to have a lot of, I don't know, let's say traffic accidents, or maybe, I don't know, people shooting guns and so on. This will not be easy to obtain. So this kind of data is not easy to obtain, and we cannot start to shoot people on the street in order to collect data. So this is not a viable way to collect data. So typically we use only normal training data. So we collect images with what is normally happening in a scene, and then when we see some event that is unfamiliar or unusual, we label it as an anomaly. So this means that traditional supervised methods are not directly applicable, but we still rely on this hypothesis that abnormal events should occur rarely. So then we have a lot of normal examples that we can collect for training. Okay, and then the task is formalized as outlier detection. So we learn a model on the training data, and all the samples that are outside the training data distribution that we learned are outliers, and they will be labeled as anomalies. Okay, so common approaches are to learn a model of familiarity or model of normality from training videos, labeling the events as abnormal that deviate from the model. There are also some approaches that are unsupervised, that do not use training data at all. So we were not going to discuss about this. We're going to discuss about this approach based on convolutional autoencoders. So the whole framework is actually the application of autoencoders with a classifier on top, but it's also a nice design of this application in order to obtain a useful model for anomaly detection. So the whole pipeline uses some pre-trained object detector to detect objects in the video, and then we take frames at specific time intervals, and we compute, for example, so the object detector is applied on frame t. Then we also consider the same bounding box at frames t minus 3 and t plus 3, and we compute the image gradients here, and here we take the appearance of the object. So the first part is related to the fact that abnormal events can be related to some abnormal motion, like people running, and here it's, for example, people usually walk, so people running can be abnormal. And also related to the appearance of the object. So it could be, I don't know, a person that is dressed like a thief, or I don't know, a car that has a different appearance, although it's driving by slow or something like that. So anomaly can be related to both appearance and motion information. So we're trying to model both of these in the framework. And here we have some convolutional autoencoders. So the first part of the training process is to train the autoencoders to reconstruct the inputs. And once we train the autoencoders, we take the latent space representations of these three autoencoders, we concatenate them, and then we go to the last part of the processing pipeline. So here we take these vectors. So one vector of concatenated latent features is represented here as a data point. So we have some, and this recall that all these are learned from normal training data. So all the points in this space are supposed to be different normal events, but here what we do is we cluster these normal events into different clusters. So we obtain some rough types on an unsupervised way. We obtain some rough types of abnormal events, and then rough types of normal events, and then we train a multi-class SVM on top of these clusters. So for example, a multi-class SVM means we train a model to discriminate these abnormal events in red from the other normal events. So we have normal events here, we have normal events here, and we train an SVM to discriminate between these and the others, and we do the same for each cluster. So actually what we do here is we have, I don't know, a number of clusters. We interpret the clusters as ground truth classes, and we have trained the SVM on top of them. Okay, so essentially, ideally, we would want to learn to discriminate between normal data and abnormal data, but instead we're trying to discriminate between some type of normal data and some other type of normal data. So this is just trying to build a supervised model without having access to abnormal data. Okay, so then each SVM produces, each binary SVM produces a normality score for each cluster. So ideally, if we at inference time, if we get a normal example, let's say a red one, then it should have a high score for this class and a lower score for the other classes, and it should be labeled as normal. But if we get an abnormal event, then all the SVM models will produce lower scores. So then the corresponding event will be labeled as abnormal. So okay, so I'm not going to detail much more about the framework. I just want to give you a general idea. And okay, so these are some results of after training the autoencoders on different data sets. And here we see the input of the autoencoders. So this is the appearance autoencoder, the input and the corresponding output. And if we look at the normal data, it is able to reconstruct the examples quite well. And for the abnormal data, so for example, in this data set, we have people in a pedestrian area and people with bicycles that are forbidden to go in the pedestrian area. So we can see here that for the bicycles, we have a bad reconstruction for the autoencoders, which is good for us. So we want to have bad reconstructions for abnormal data and good reconstructions for normal data. And here, I don't know, we have a person that is fighting, person that is running, and so on. So we have worse reconstructions here than in this case. And we also observe the same for motion. So here we have examples of normal motion with people walking, and we see good reconstructions. And for people that are running or doing other actions, or here we have some motorbikes, some bicycles, and so on. So these are the gradients. So these are actually moving pretty fast and are taken at an interval of 3 frames. So the gradients look like this. And we can see that the reconstruction is farther away than, in general, it is farther away than the input. Okay, so yeah, this is just some intermediate results that tells us that the autoencoders obtain good reconstructions for normal examples and worse reconstructions for abnormal examples. And then we actually test the entire pipeline on anomaly detection on 4 data sets. And we use as metrics the area under the receiver operating characteristics curve, which is computed with respect to the ground truth frame level annotations. So these data sets contain videos, and in each video we have the label for a frame, if it is normal or abnormal. So this is the labeling for the test data. For the training data, we have only normal examples. And here we have some ablation results of our framework. So this is just the framework with a simple one-class SVM model. So this is a model typically used for outlier detection. And this is the convolutional autoencoder applied at the frame level, so without object detection. And we obtain an AUC, an area under the curve of 72.4%. Then if we add our framework with k-means clustering and 1 versus rest SVM, we can improve the anomaly detection score. Here we have some results with pre-trained object detection features. So our object detector outputs the bounding boxes and the classes, but we can also take the features from the object detector for the corresponding objects. And if we use these pre-trained features, we obtain a better score than the frame level. So if we use the object detector, it is useful. But instead of using the pre-trained features, if we learn the features with convolutional autoencoders, then we obtain better results. So this is the convolutional autoencoders based on appearance information. So it already gives us better results, but we also have the autoencoders for motion features, and this gives us another improved result. Then here we have the combined autoencoder features, but instead of our k-means and 1 versus rest SVM, we use the classical 1 class SVM, and the score is not as high as our full pipeline. So the model that we actually described earlier is this model on the last line, which achieves this performance, which is still state of the art on this data set. And yeah, we have here the frame level AOC results with other compared with other state-of-the-art models. And we also have some frames where we show the detections of our model. So this is from Avenue dataset. So a person that is running, a person that is throwing an object, and a person that is walking in a wrong direction. So these are all labeled as abnormal. Here we have bikers in pedestrian areas, a person stealing a backpack from another person, a person jumping, and some people fighting. Here we have bikers in pedestrian areas and skaters. And here we have people running as abnormal activity. And we also have an example with a video where we can see how the autoencoder, the pipeline based on autoencoders and clustering and 1 versus rest SVM can detect this abnormal event. So this is, I think it is a simulated event, but even so, it looks realistic, and the model can detect it as an anomaly. So we see the detections in green. Okay, and we have some closing remark regarding this application. So we've seen that the autoencoders obtain better results than the pre-trained detector features, and it also, as an additional remark, it is useful to focus on the object to improve accuracy. Okay, and this was the last slide of my presentation. Yeah, I think I answered to your question. So the clustering is done with k-means clustering, and I think in all the experiments we set the number of clusters to 10, so k is 10. So in this illustration we have 4 clusters, but actually in the experiments we have 10 clusters. Okay, so yeah, I'm finished with the slides. Let me know if you have any questions about the presentation. Okay, I see that there aren't any more questions. Oh, actually, we have a question. Yeah, you will see the project requirements, but actually I mentioned, so probably Matei, you were not in class, but I mentioned that you have to do a comparison with SOTA. So yeah, that was mentioned, but probably you were not attending the lectures But anyway, yeah, I can try to make some written document. So in the Kaggle competition, for example, we're going to make a, yeah, minimal list of requirements for you. Yeah, you can also do so when you have supervised data. You can fine tune the autoencoders. So yeah, it is possible to fine tune the autoencoders. Okay, you're welcome, Matei. So okay, let's wait for 1 or 2 minutes if um, okay, so I think you had enough time to think about questions. So can you use transfer learning? Good question. I think so. You will be able to do it, of course. I don't see a problem in using transfer learning. So yeah, it is possible to do transfer learning. I think you're probably referring to the Kaggle project, then yeah, then the unsupervised project. So in the unsupervised project, you can do unsupervised transfer learning, like you train some autoencoders that are unsupervised. But okay. Okay, so I see no further questions. So thank you guys for participating and see you next week. And I hope, not sure that if I'll be able to do it until next week, to launch the Kaggle competition for you. If not, I'm going to do it certainly in 2 weeks from now. Okay, thank you and goodbye. See you.